Okay, so let's FOIL this out. I'm going to be doing the as h approaches 0, but I'm going to rewrite that numerator as 9 plus 3h. No, that's a lie. Not 9 plus 3h. 9 plus 6h plus h squared. Because I can square a binomial pretty easily. 3 plus h quantity squared. Okay, we shouldn't. Okay, it's helpful if we can do something like that pretty quickly if we know how to square a plus b. Minus 9 all divided by h. Okay. So that's definitely something we can do to rewrite it. We've got a different look to the function now. Let me go ahead and grab that because I'm not going to have enough room. Let me grab this guy and go. Oh, you're all right. Okay. Now, after I do that foiling, I should probably be looking and seeing any like terms. I can take the 9s out. And so I'm looking at this 6h plus h squared all divided by h. And unfortunately, that's still 0 over 0. Anything else I can do to rewrite this? Go ahead. Factor out an h, yes. So if I multiply or factor out an h in the numerator, then the h in the numerator and the h in the denominator divide away. And so now the problem looks like this. And the interesting thing about this problem is this much simpler expression that I've now written this problem as is 100% equivalent to what we started with. It's just another form. And I know that because everything I did is algebraically, mathematically legal. I only replaced things with equivalent expressions. So this expression is equivalent to this expression. All I did was rewrite out the parentheses. And then this expression here, where the 9s were, is equivalent to this expression. And this expression is equivalent to this expression. And this one is equivalent to this. Nothing's really changing. It's like the same person who puts on like 5 t-shirts and 4 pairs of pants and then progressively takes off, 3 of the t-shirts and 2 of the pair of pants. It's still the same person. They look different. They have different outfits on every time, but we're still talking about the same person. We're still talking about the same function. And once you say, well, how far do we go? Until substitution works. You go until substitution works. And substitution finally, and notice as soon as I realize substitution's working, I'm not limiting anymore. I am not taking the limit. I'm just substituting in and evaluating. Yes, sir. Say that again? Sure. Okay. So this is what, okay, because when I take 3 plus h times 3 plus h, because it says 3 plus h quantity squared, I know it's going to be that, right? If I take a plus b times a plus b, I'm always going to get a squared. I'm going to get 2 times the product of a and b, and I'm going to get b squared. Okay. And 2 reasons I didn't write it out. Number 1, lazy, 100%. Number 2, we need to save time some places. There's going to be there's a big element of this that there's going to be a time consideration. So we need to cut corners as much as we can, and squaring a binomial is absolutely one of them. All right, so we're trying to do limits. We're working algebraically. We're working without graphs. We're going to try substitution. If substitution works, everybody's happy. If substitution falls apart, we are going to have to look for other strategies, other ways to deal with 0 over 0, factoring, working with a table, expanding using some algebra. All right. Great, make a note here. Next page. All right, let's go to the problem actually right underneath it. Let me go back here to, oops. Why does that keep locking me out? I wish it would just let me stay in here. All right. Sarah, I want to come back to you because you actually said something that I'm going to be super excited about right now. Let's take a look at number 16. And Sarah's like, I don't know what you're talking about. Number 16, substitution, 0 over 0, right? You plug in a 1, you get a 0 in the numerator, you get a 0 in the denominator. 0 over 0, bleh, do more work. No expanding. No factoring. I need another algebra tool. Sarah, do you have an idea what we're going to do here? We're going to multiply by the conjugate, and the conjugate is we focus on the radical expression, and so I'm going to multiply this function in the numerator by root x plus 1, and the exact same thing in the denominator. Why is that legal? Because I'm the math teacher and I said so. No, Yash, why is that illegal? It is technically, it is not even just technically, it is. We're just multiplying by 1. Multiplying by 1 doesn't change anything. I multiply by 1, I still have the same value. So all I want to do is I'm just going to give this function a makeover. Essentially, every time we're dealing with a 0 over 0 and we try to like re-represent the function a different way, we're giving the function a makeover. It's still the same function, but it's going to look different. Now, conjugates are a trick. It's straight up a trick. And you're going to know that that's a good plan for something to do because it's going to help you whenever you have an expression with a radical. When you have that expression with a radical, that's the way you start, like, I can't factor. I can't factor and I can't expand. Like if I'm squaring something, I can expand. Cool. If I've got something, you know, expanded out, I might be able to factor it. I might be able to take out a common factor. Roots don't have a lot of things you can do to them. But watch what happens on this if you multiply by the conjugate. Let's look at the new function. I still have the limit as x approaches 1. Now watch what I'm going to do. In the denominator, I'm going to FOIL those conjugates together. I love to multiply conjugates because multiplying conjugates are super easy to multiply, just like multiplying a plus b times a minus b, which is our favorite conjugates of all time. What happens when you take a plus b times a minus b? What do you get? Too slow. Come on. A plus b times a minus b, you get, thank you, a squared minus b squared. Always. So root x plus 1 times root x minus 1. Sorry, I'm pointing them to the wrong way. So root x plus 1 times root x minus 1. I'm going to get root x squared minus 1 squared. Which means, and I'll probably never write that in between stuff, I'm going to get x minus 1. Now, here's why that makes me super happy. I'm kind of hoping eventually I'll be able to cross something out. Essentially, the thing that's making the numerator and the denominator 0. Well, if x is approaching 1, the thing I'm going to hope that I'm crossing out is x minus 1. And look, there's an x minus 1. I am going to let these two numerator factors just sit next to each other. Because what I want to see, if I FOIL these, I won't see it anymore. I want to see the common factor to divide away. Hello. Okay. So the twos that are not conjugates, just let them sit next to each other. What you're hoping is that one of them is going to divide away, because one of them is going to match the denominator and divide away. That's what happens in conjugate multiplication, using that as a trick. Bam. What's the value of my limit? 2, right? Because I'm going to take root x as x approaches 1. I'll get 2. Okay. So we FOIL the conjugates, but the non-conjugates, we let them sit next to each other. We just let them sit there, hoping something is going to cross out. These problems have a certain sort of pattern to them. We're kind of looking at the different scenarios that we most commonly run into. Does that mean we may not run into something that's weird? Absolutely. We actually have other ways to solve these problems. Later, when we learn more about derivatives, we can come back to these 0 over 0 problems and attack them a completely different way. Sometimes it's easier, sometimes it's not. So when we run into a 0 and 0, you should start kind of going down your checklist. It's kind of like your toolbox of like, okay, what can I do to a 0 over 0? Like your MacGyver. You guys know who MacGyver is? No? Okay. So there was a TV show in the 80s, I think. I feel like it was in the 80s. It may have been in the 90s. I don't know. 80s or 90s, called MacGyver. Okay? And so what MacGyver did is that he would always like figure out how to save the day, but he would like use weird stuff to like build something to fix. So like, I'm like, I need to defuse this bomb and I need to use a Post-it and a nail file and a piece of chewing gum, and he would do it. Okay? And that's MacGyver, right? So anytime you kind of have to do something weird, somebody of my generation would be like, oh, you're like MacGyver, you know, you're just sort of figuring out how to do it. These limit problems are kind of like that. You kind of have to be MacGyver and be like, all right, what's in my toolbox? Do I need to use factoring? Do I need to use foiling? Do I need to use conjugates? What can I possibly do? The problem setup will probably suggest something to you. Okay. So what do you think we're going to do? First of all, 17, how do you know we have to do something special? You have a root there, and what? Double check. What happens when you plug in 2? You get 0 over 0. Always check first. Always check first, because it's likely, I've seen it happen. Here's the problem. It looks like it's going to be something where I've got to use a conjugate or do something crazy, and substitution works. We only have to worry about doing all this crazy algebra if it's a 0 over 0. So this is a 0 over 0. So we are going to use a conjugate. The numerator this time is the expression with the root. So the numerator is where we're going to build the conjugate. So I'm going to multiply by 3 plus the root of x plus 7 in the numerator, and 3 plus the root of x plus 7 in the denominator. All right, try that one, see if you can finish it. Meanwhile, I'm going to see something, so just everybody bear with me.